Hey everyone, welcome to my stream. Hey RepNop. So RepNop is telling me that he started streaming and he just actually finished streaming about 40-ish minutes ago. Oh, thanks Slick Rick for following. So yeah, what's this? RepNop says that he decided to work on this issue here. Okay, so it's actually on Rustlang itself. Oh, that's pretty awesome. So you got to delve deep into the Rust compiler. That's really cool, man. So what's your I guess RepNop is let's see here. I was already following you, right? Follow. Oh no, I wasn't. There we go. I'll catch your stream the next time you're on. For any viewers who are looking to follow another dev stream, you should definitely check out RepNop's stream here. REP_NOP. So did you have fun? Oh, you have a few actually. That's awesome. Good stuff, man. So tonight I want to kind of pick up where I left off last week, and that is to say, let's see here. Actually, let me switch into release. By the way, I did a little bit of work on trying to figure out why the debug, like why does my emulator run so slow in debug? Because I hit about like less than 10 FPS in debug, and yet when I run in release, we're looking at speeds of like, you know, the thousands of FPS. So this is such a huge difference. Slickrick says he did. Oh, okay, you just watched RepNop stream. Let me see here. Oh, RepNop says this is the name I used to stream. I actually promoted your stream a bit. Ah, thanks, man. Really appreciate it. So that's where you come from, Slickrick? That's really nice of you. So yeah, what I was saying was, actually I think I need to just change my Windows settings. Give me 1 second. Where did I put that stuff? Options here. Okay, let's try that again. Basically, when I launch, there you go, you got the window here, got the debugger here. And you notice like here I'm hitting like 3,000, let's see, let's say I'm averaging about 2700 FPS. And that's cool, right? But when I run in debug, I was like wondering, like, why is it like such like 2 orders of magnitude slower? You know, if I run here, see, and it says here 10 FPS, and in fact it's even slower than that. It's because I actually like have a limit on so that I don't have delta times that are too large. So I basically clamp it so that it doesn't go much lower than 10 FPS, but it's just crazy slow, right? Well, after a little bit of profiling, it turns out that, and it's not a huge surprise, but I mean, let's just say if I had to guess where the slowdown was, I would have guessed that it was this. It was the fact that I have these, it's my breakpoint system. Instruction breakpoints, not too bad, but it's the fact that I have watch points or data breakpoints on every single write or read of every address, So I have here my memory bus. Every read and write calls a callback, which in my debugger is hooked up. Where's callback again? No? Where did I put my callback? Oh, that's why. There we go, register callbacks. So I have here some callbacks for the read and write, where I look up for whether there's a watch point, a read or read write, or write, read write, watch point. So I can break into the debugger. While this, of course, for every single read and write just takes a phenomenal amount of time. So just to show the difference, like if I comment out the callbacks here so that I don't call them for every read and write, so that gives me a bit of a speed up. Yeah, so RepNob says those must be insane optimizations doing. And honestly, it impresses me, And I thought, maybe I could. I just messed around a little bit with it to see if I could get it there. So see, still not quite hitting the mark there, right? But if I actually disable, it's like I need both. It's a combination. I need to disable these breakpoints and basically effectively just disable checking breakpoints altogether. So over here, these are where I check instruction breakpoints, right? So let's just say I block this off. Now let's take a look at what it looks like. See, now we're getting at something a little bit more decent. You see, we're at what now? About 7. It's gonna go up to about 700. So that's quite a bit different, right? 750. Slickrick asks, "Oh, do you use one of those ergonomic keyboards?" Yes, I do. This is basically it's the Matsias Ergo Pro, and it's the reason I got this is because I was a big fan of the Microsoft ergonomic 4000 keyboard, but the thing is, they actually cheaped out a bit on their materials over the years. The original versions that I used to get were still rubber domes, but they were made better, and they were actually a bit more expensive. I remember when I was getting them, they were about 60, 70 bucks, I think even 80 bucks initially, and now they sell them for like 40 bucks, but they like reduced the quality of the keyboard. I remember like how the space bar would have like these 2 springs in them, and then they reduced it to just 1, things like that. And so I kind of got tired of that and the mushiness of the keys. So I decided to buy myself, I wanted to get myself a mechanical, but actually split mechanical keyboards in standard layout are actually not that easy to find, or at least they weren't. Now there's a couple more, but this was the first one that was like closest to what I wanted. And it's not a perfect keyboard. I have a couple of grievances, but it gets pretty close to what I want. So yeah, back to the optimization. So like here you see we're averaging about 600 FPS, right? And that's just by effectively disabling breakpoints. In fact, what I noticed was that if I come back and I put these in, and I just go to my breakpoint class, and this is gonna be nuts, right? This get function here. If I check, this was actually kind of surprising. So if I do this, right? So I say every time, so for every instruction or data breakpoint, I call this one function get, and I give it an address. And this here effectively does a lookup in a map, which, you know, maps are not fast, but I need it to be ordered, so it's fine, right? I keep this. I need it to be ordered because I display my breakpoints and I allow you to disable enable them. So just to keep things simple, I use a map. Now, by checking if there are no breakpoints, I skip this code here that does the find for in the map. Now, consider a map that's empty, right? So this find here should really do not much, right? The map is empty, it should return an end iterator, then compare that to the end, and if this will be it will be equal to the end, and so I'll return null. So this code here should be very, like, in my mind, pretty fast. But just adding this here, let's just see what that gives. That's the only change now. I reverted my 2 other changes. And I think I tried this yesterday and I noticed that it was quite a bit faster. So you see, look, we're going up here to about, say, 240, 250, 270, 300. Well, we can't really, okay, so yeah, that's it. So we're about 375. So that's quite a bit of a difference, considering that if I just remove these 2 lines, we drop down to like less than 10. So RepNob says, are you just checking each address you interface with when you check for breakpoints? Well, I actually think I'm gonna head off for tonight. Just want to pop in and let you know about my stream and say hi. Oh man, thanks for saying hi, and also it's cool that you're streaming. I'll totally watch that. Hopefully I'll catch it next time you're on. But just to answer your question, am I checking each address? And the answer is yes, right? That's sort of the idea. And there's different strategies I was thinking about for optimizing this. But I just want to say it's kind of interesting that, like, how much more expensive it is to do this over just, you know, doing a little check. Now, this is not a good enough optimization, because I mean, as soon as I add a breakpoint, I was trying this, right? So like, here we are, we're running at pretty decent speed. We're at 218 FPS, whatever. And then I add, like, I come in here and I add 1 breakpoint, you know, on address 0 or whatever. And then I continue, and boom, we just drop down to 10. You know, so, and if I break again and I delete, delete breakpoint 0, and then we're back to like good speeds again. So this is definitely not something I want to keep. But anyhow. So yeah, thanks RepNop, and hope I catch you next time. So anyway, all that to say is I don't really have a great solution just yet for this. I'm quite impressed at how this same code is just insanely fast in release compared to debug, even though I'm doing exactly the same accesses and everything. And I know a lot of this code gets inlined, but inlining is not the full story, because I actually also messed around with forcing inline, and I checked, you know, that it actually was inlining, and it did, and that was not enough to get it fast. It's more than that. There's a whole bunch of optimizations going. I also suspect that linking against the debug CRT, where there are a bunch of checks being done, a lot of asserts that are being done in map and these associative containers, are making it that much slower. It's really showing for that many accesses per instruction. So, however, I can run in release with debug like this, and I can get quite far with that. So I will use that. Oh, and look, another thing is you might notice here, those who've been watching my stream, that the rendering actually has gotten a lot nicer than the last stream. So let me show how that happened. I'll bring over my Git extensions here. So last stream I did this commit here, fix rendering. It had to do with changing the way the shift register works so that it's actually not a roll register but a proper shift register, and also making the line drawing cycle accurate by making it do the timer update and the shift register and the B movement 1 cycle at a time. So that was cool. I added some little change also last time for ignoring comments in the options file. But here is a change I made, what, 2 days ago? Yeah. And here, get rid of render flickering by drawing all lines once after clearing screen at 50 Hertz. So basically, I just had this realization. I was just looking at my code and I was thinking about this, and I was like, what I was doing was in my render loop, I added this hack, right, where I check that, you know, every 50, like every 50, what am I trying to say? 1 out of 50, at 50 Hertz, sorry, at a rate of 50 Hertz, I would clear the lines that I had to draw, but I would also clear the display. And then after that, I would start drawing the next batch of lines until 1/50 seconds has passed. A 50th of a second, right? So the thing is, what would happen here is that I would end up clearing the screen, and then over the course of the next 50th of a second, we would start to draw lines. And so what you would see is kind of flickering, because it would go dark, and then some lines would be drawn, and then it would go dark, and some lines would be, like, the lines for that screen would get drawn over time. And what I did is I realized, instead of doing that, what I should be doing is, once every 50 seconds, is clear, draw all the lines, clear the display to black, draw the lines I have for that 50th of a second, then clear the lines and leave those on screen for that 50th of a second until the next 50th of a second, where I will once again clear the display, draw the next batch of lines that came in since the last time, and clear that. And just that, you know, gives us kind of persistence of lines on screen, which just looks like way better. So it looks like this, right? No darkening and flickering like I had last time. Which, you know, is pretty cool. So that's cool. And another thing, I believe I did this on my laptop. Let me see here. Can I I'm gonna pull with merge. Apply stashed items, yeah. I think I just made one small change. Yeah, get debugger, don't break on start, and disable trace by default. Yeah, it's super minor. It's just, instead of always starting with a debugger there and waiting for me to disable trace and continue, it now just starts right away, like this. Because I'm at the point now where I just want to run the game, and I don't need to, like, start from the debugger at instruction 0, like, or at the first instruction, and then turn off trace and continue and all that. So it's very minor, but still helpful. Now with that, I decided that, you know, that it would be fun to try and launch my emulator and just try different ROMs. And let me just show you what that looks like. This is Vectrexy. Let's open up a command prompt here. So let's say from here, I go into build, release with debug info, Vectrexy. So that launches Vectrexy, as expected. And if I do this, and I go into my ROMs, and let's say I choose Scramble. This is something I tried, right? So it's gonna load, and now eventually it's gonna go to the Scramble's initial screen, and then I'm gonna get an exception, as you'll see, there. And the exception is that there is an instruction I have not implemented yet, which is subtract with carry, in this case register A. So this is something I knew. I haven't implemented the entire instruction set, but as it happens, I've implemented enough of the instructions to be able to start the Vectrex, render the fonts, and, you know, show the Mindstorm intro screen and the you know, selection screen. And that's it, right? And so I'm not surprised at all that different games would then, you know, like in this case Scramble, would end up using an instruction that I have yet to implement. So if I go to opcodes here, SBC, so yeah, these are the SBC instructions, subtract with carry, and sure enough, I don't actually have any of that what is it, SBC? Yeah, I'm not implemented SBC. So that's one of them that I'm gonna have to implement. But that's, you know, that's for Scramble. But there are other games in here. Actually, I wanted to try, for example, one that I really love is Ripoff. Let's see how far we get there. Oh, and here we go. So this one here, Ripoff has a more interesting assertion, which is read from unmapped range at address 8A80. So that 8880. That's very interesting. Where does that fall? Oh, it falls right into the middle of what's known as unmapped memory. So that's strange, right? Like that again can be a few things. Optimistically, this could be that the game just does actually read in invalid range, unmapped memory, which would be a bit strange. Now that's me being optimistic, and it's unlikely. More likely, what it is that either I have a bug in my CPU implementation, and when that happens, sometimes the CPU instruction will do the wrong thing, and eventually that will lead to the, you know, either I'm executing an instruction that's not valid at all, or like for example interpreting data as instructions and then executing them, and then you end up doing something funky like accessing addresses that are completely invalid, like in this case. It could also be that another possibility that I have not implemented at all is bank switching, right? Perhaps, because if you look at this 8A80, I mean anything inside this range, depending on how the cart is wired up, perhaps they decided, you know what, let's use this illegal address range to do some bank switching. And maybe Ripoff has multiple banks of RAM, or ROM, in fact. Yeah, ROM, I would say. Maybe the 32K is not enough, and they have 2 banks or something, and they designate this address for. Is it actually a write? No, it's a read. So actually, that's normally for bank switching, you're expecting a write to some address. So read is a bit strange. I don't know. It's fine. I'm not really interested in debugging that right now. What I would like to do right now is to implement the input so that I can see what it would be like to get into the default game, right? Into Mindstorm. Oh, another thing I noticed, if I just break here. So I did get the rendering to work, however, it's not actually correct. And what I mean is, you can notice here there's kind of like this slant, right? It's like being written in italics. That's not correct. So if we take a look, yeah, here. This is what the Vectrex intro screen is supposed to look like. And notice that all the letters here are perfectly straight. Whereas for me, they're very much not perfectly straight. So what that probably is that since writing is not done using the timers, but in fact is done by ignoring the timer, like disabling the timer, and is done by turning on and off the beam pretty much by relying on the number of cycles that instructions take. Now, we looked at this code last stream when we got this working. It really is kind of like turn on the beam and execute some stuff and wait and then turn it off. And all of that is like cycle counted. So, you know, the programmers who worked on the BIOS for these routines were literally counting instructions saying that this here will take this many cycles, this will take this many cycles, and then like say, oh, on our way, like writing through is one thing, and then on our way back, they need to make sure that the same number of cycles elapses so that the beam gets back to the beginning so they can start writing the next line. And the fact that it's angled this way tells me that I most likely have some inaccuracies in my cycle counting. So, like for example, maybe my CPU is not returning exactly how many cycles have elapsed correctly, and so then that might end up showing up it would end up showing up like this, where we get an overshoot in the beam moving this way. So that's something I need to investigate. But you know, given that this is the kind of thing that's mainly done for rendering fonts, I don't believe we're going to see this effect as much for the in-game objects and stuff, because those tend to use timer 1, just like these lines on the outside that look pretty good, right? So things based on timer 1 should work, because the timer 1 is simple. You know, the every 2 CPU cycles counts for a clock, and you know, it's anyway, maybe I'm wrong, maybe it's all related, and we'll notice that objects are skewed as well, and it'll all depend on me getting the cycles returned from the CPU correct. But anyway, we'll see what it gives. For now, I just would like to get into the game, and to do that, I need to implement input. So that's a lot of talking and no programming. So let's see what we can do about this. Now, to be honest, I have no idea how to implement the input for the Vectrex, and I'm hoping to find some information on doing just that. And unfortunately, I didn't get a chance to do that before the stream, so I'm going to be doing a bit of that here on stream. Last time we did look a little bit at how the BIOS does it, and we saw that it is related to like this function here, the read button masks, and we saw that internally what the BIOS actually does is it uses the port A and port B of the VIA chip to get those readings for inputs. But I really need to get some very clear information on that. So let me just do a little bit of searching here, see what I can find. Let's search for, what should I look for? Searching for button, getting lots of hits here. Let's see if there's anything in here. Joystick Tandy, interesting. Let's feed this into a list box and take a deeper look here. They're the pinouts. So that's interesting. Read button masks.htm. So I think this is basically going to show us like what the routines actually do, the BIOS routines. So that's the function we were just looking at. So it might be interesting to read this. Both of these routines read the button states of the 2 joysticks and return their state in the following RAM locations. So that's the state of the, there's actually 4 buttons and an analog joystick. So joystick 1, button 1, 2, 3, 4, joystick 2, 1, 2, 3, 4, contains current state of all buttons. Then C810 contains state of all buttons from last time these routines were called. Oh, that's cool. And if read button's mask was called, then this is ANDed with the passed in mask. Contains the same information as this to there. If read button is called, the result will be the same as read button mask with a mask of FF1. Okay, I mean, I don't really care too much about this, because this is actually just the way the BIOS is written, and it's to help programmers. What I really need to understand is what this function is doing internally. So that's not really answering that question. Okay, what's this here? Okay, this is just an example that shows how reading buttons works. Again, more of a higher level thing, so it's not super interesting to me. I just, okay. Maybe Frogger. I know that the Frogger game has a lot of low-level stuff in there. Let's take a look at this. Not that. This is the source. Button. No. Okay, there's just some text. Wonder if the ASM has anything in there. My read buttons A. Button 4 of joy 1 press. No, can easily be changed to any other button. It's just a bit. So this guy who wrote the Frogger game, what's interesting about what he did is that he effectively rewrote a bunch of bias routines so that he could squeeze out a bit more performance out of his game than using the, because he writes it everywhere that basically what the bias routines do is they waste a lot of cycles. And I mean, the thing is, there's only about 30,000 cycles per frame, right? So really important that cycles are not being wasted if you want to make a game that runs really fast. So let's see. Read buttons, although he is actually jumping to the read buttons routine here, so. Okay, so nothing useful there, unfortunately. So what about this here, interface? This pretty much describes the working interface as built. Interesting. What is this for? Some interesting information, but not what I'm looking for. What I could do rather than this is, let me just take a look here. Comparator. Let me look for that. Look, finding some things here that might be more interesting. Technica.htm. So let's feed this to listbox. Okay. Following information was extracted from the Vectrex technical manual. I've redrawn the schematic, which I don't have, and added the table to make it easier to understand. If you have a basic understanding of electronics, you should be able to convert another joystick to use the Vectrex without too much trouble. See. Yeah. Guts. Okay, here. Joystick pot positions are sensed by a successive approximation process. The MUX chip selects each joystick pot input line and applies it to the plus input of a comparator. At the same time, the MPU generates digital words that are changed to voltages by the DAC and current voltage converter mentioned previously. These voltages are successively successively applied to the comparator's minus input until the MPU generates. Okay, getting a bit closer. So the MUX, that MUX chip there that we were talking about that the VIA uses, it selectively couples under MPU control the output of the DAC current voltage converter to one of 4 places and is used to selectively couple the inputs from the joystick pots to the voltage comparator. Okay. I wish I had this image here. Maybe I will have to really understand what the BIOS is doing and kind of figure it out from there. And reverse engineer what it's trying to do with the read buttons. Let's keep this in mind. It's supposed to store, so into here, the state of each button. So let's see what it's doing. C812. Okay, so what is this what is this variable? C80F. Okay, so there are actually names for all of these. Vec button state, current state of all joystick buttons. Previous state. So these are the 2 that are used as bit masks for the 8 buttons. I think each bit, right, represents one of the buttons for the 2 joysticks. So this will store the previous, this stores the current, and then you can actually get a reading for each one if you want. Current toggle state of all buttons. Current toggle state of stick 1, button 1. Current toggle state. So C812. C80F, as we were saying up here, contains a current state of all buttons. 1 is depressed and 0 not pressed. And A10 contains the state of all buttons from the last time. And if read button's mask was called, and this is ANDed with the passed-in mask. C811 here, current toggle state. Contains the same information as C812 to C819. Okay. 2.4 like this, right? That's a mistake. Now, if read buttons is called, the result would be the same as read button mask with a mask of FF. And a 1. Okay. And a 1 will return, will only be returned if the button has transitioned to being pressed. If a bit is 0, then the current state of the button is to be returned in the appropriate RAM location. 0 not pressed, 1 equals pressed. If a bit is 1, then the appropriate RAM location is set to 1 only on the depression transition of the button. Ah, okay. And additional calls will return 0. So basically they're offering an interface where you can check whether a button is currently down or up, or whether it went from up to down or down to up, so you can detect the edges. Okay, and I guess that's why there's these extra, like this here is just the current exact state, button up, button down. So that's really what I need to focus on, is this vec button state, 80 C80F, which I don't think we're going to see in here, C80F. We're going to see vec button state exactly. So mask out always buttons. That's what they call them, the always buttons. The ones that, this is the state of the, whether they're down or up. So and a, oh, that's in case you called it with a mask. Okay. So it's only actually done here. That's strange. Vec button state. Mask out always buttons. Store A to the vec button state. But then what actually updates this value? What about previous buttons? Nowhere. Okay, I guess it's because, yeah. Okay, so it's done with some math. Basically, like for example, here we load vec button 1 into X, and then into A we say take X minus 3 bytes. So here minus 1, 2, 3, and that gets the vec button state into A here. So we read that so that we can store it into minus 2, which is this one. Okay, so that's why we're not seeing it. So minus 3 we can see over here save buttons. So there, that's where we actually write into vec button state. Here. So let's see now. Working backwards from there, this is all the logic we need to read the current state of the buttons. So let's see. Sound chip register 0E to port A. Sound chip register 0E to port A. Okay. So I know that we have to go through the sound chip to access the inputs. And looks like on the sound chip is connected somehow to the inputs through this register E. So that's interesting. Let's keep that in mind. So we store that into port A. Then we go and load 19 into A and 01 into B, because we're going to be writing that. We're going to be writing 19 to port B. So, and then what about B here? Okay, so basically we just need to 19 and then 01. So mux off, let's see, bdir on, bc1 on. So that comes from basically $19 does this, whereas $01 does this. That's what we have in here in D. So let me just double check this. 19, if I go to here, so 19 means we are setting bits 1 or so 0, 3, and 4. So we enable the mux. No, sorry, we disable the mux. Then we enable sound BC1 and sound B direction. So this is on and these are on. That's exactly what we have here. Sound B dir on, BC1 on, mux off. Really need to know what these mean. And so we do this, and then we do a NOP, right? After we store that, like after we switch into this mode, we NOP so that we give the chip enough cycles so that it gets the value that was previously written here, sound chip register 0E. So this should select sound chip register E from the sound chip. And then after that we write 01, which basically gets us to disable mux alone, and then we basically are turning off these two here. So BC1 and B dir are off, which is what we see here. The mux just remains off. It's really the important bit is right there. It's turning on this and then turning it back off. Now we do that, and then we clear, what is this, via DDRA. DDRA to input. What's DDR? Oh, okay. Really? Oh, I see. Okay, that's very interesting. Hey, Claycree. Thanks for joining. Claycree says it's his first time seeing assembly on Twitch. Well, I mean, I'm generally programming in C++, but I need to read assembly to understand how the Vectrex works, right? Because all the code is in assembly, in 6809 assembly. So yeah, I'm not even like really an assembly person, you know. I didn't really learn assembly much, you know. I didn't start in assembly or anything. I learned it at school and then, you know, learned a bit more at work in order to read disassembly and stuff. But this project has really forced me to learn even more how to read assembly code like this. It's been an interesting experience. Okay, so what I'm reading here, so the data direction register, normally port A, we write to it. We don't read from it, right? So we're always writing to it so that we can like do drawing and stuff. But now we would like to read from it to get the values of inputs. So that's what that's about. By clearing this here, we're saying, hey, set the data direction register for A to input mode. So we can read read joystick values. So we do that, and then we load 0901. So that's what this is about. So we're going to store 09 here. So store A09. So here saying B dir off, BC1 on, and mux off. That's what this is. So actually what I'll do is I'll do this, $09. So that's sound B dir off, but this time BC1 on and mux off. Okay. So we store that in there. Again, we wait. So ostensibly, when we set this mode, Okay, so I guess I kind of understand now. Is the beater, this beater here is the direction of data to the sound chip, I assume. Right? Sound beater meaning probably the direction for register B. Yeah. So this means we're going to be sending data to the sound chip. If we turn it off, it means we're going to be reading data from the sound chip as well. So it's kind of like we need to do two things. We need to say we're going to be switching the mode for register A into read, to input mode, and we also need to say that the sound chip's direction will be off, which probably means read as well. Again, I'm just kind of extrapolating here. BC1 on, still don't quite know what that is. It's probably connected to the joystick pot or whatever, so I'm going to take a look at that. And then we store that in here, we wait, and now we can read the buttons from port A. Okay. And that will get us the state of the two joysticks, whether the buttons are pressed or not, right now. So, let me think here. What I'm thinking about is, obviously in terms of emulation, right now I'm just looking for the minimal amount of work I need to do to know when I need to feed the input values on port A. And I think all I really need to do for that, looking at this code, see, then we store B here to turn the B direction off. So I think it actually is the BC1 that I care about, it seems. And no, it's the combination. Basically, if beater is off and BC1 is on, like this combination here, right? Especially these two. When this is set into port B, then we want, and technically also that the data direction register says we're in input mode. When this happens, we need to be reading joystick values, button values, and storing them in A. So let me see, did I have the data direction register set up properly? So let's go to my VIA chip here. So there's data direction A. See, I'm not even using it at all. Okay, interesting. Yeah, like so far I've been totally ignoring the data direction register. So I guess what I could do, I could do it here in update. Should I do it in update? It's like a bunch of stuff I should be doing. Like, if we try to write to the data direction, if we try to write to A while the data direction register is in read mode, I'm not sure what's supposed to happen there. Like if the CPU tries to write to it. I suppose you can, but it'll just get like crushed and ignored, So like right now when I write to A, I assume that you're writing and therefore I need to update the integrators, but technically I should be checking if the data direction register is even set correctly. So let's see that. Let's start with that. We'll start with data direction register. Trying to remember here, because there's 8 bits in here, but I guess we would like to set all of them, right? What does it do again? Clear. So it clears them, which means they're all to 0, which means that it's input mode. But then does it actually set it back? DDR8 to output. There it is, FF. So technically this acts as a mask, right? For input output. You can actually, if you want, configure specific bits for input and specific bits for output. Do I need to really worry about that? Probably not. So what I can do here is something like where we write to the DDR, data direction register. I'm going to say here assert message that this is actually being either written, we're either getting a 0 here, or we're getting a all ones. And then I'll say expecting DDR4A to be either all zeros or all ones. Because if that's not the case, I'm gonna have to do something special, but I don't think this is ever gonna happen from what I've been reading. So now if I can assume that, then when we write to port A, I can say if the data direction register for port A is output, right? So all FF. Then we want to update integrators. Okay. Otherwise, I guess we'll just ignore what people write. I mean, it'll end up here, but it'll be crushed by the next update because we're going to be in input mode. Okay, so that takes care of the data direction register. So like now, if I try this should still continue to render because quite sure that it won't be set. It'll be set to 0, 0. What's the problem? Vectrexy was running. Yeah, okay, so everything looks fine. So next bit is about this writing to port B and this concept of the B direction and the BC1. I'm gonna ignore for now, although it's very important, I'm sure, once I need to do sound, but I'm gonna ignore the fact that we have this whole like selecting register E on the sound chip and that we strobe the B direction on and off here and the BC1 just to be able to select that. What I'm going to focus on instead, though, is the fact that we do this here. After we set this to input mode, we set the BDIR to off and the BC1 to on, and wait. And it's in that state that we actually need to update the buttons on port A. And then read the buttons, convert to active high, save the buttons. And then we do sound BDIR off, BC1 off. Okay, so that's all port B. So I'm going to just add some values in here. So it's bits 3 and 4. Sound BC1 is bits 3. BDIR is bits 4. So that's bit 3 and that's bit 4. Okay. And now I'm going to go into my update function. Actually, maybe I'll do it after I do the drawing. And I'll say if what? If test bits of port B sound BC1, was it BC1? BDIR off. I'll start with BDIR. Sound BDIR. So if that's off, but BC1 is on, just gonna double check. Am I actually right here? That 09. Yeah, it's 0 and 1s, so that should be good. Port B, sound BC1. So in this case, we want, and also I need to be checking that port A, the DDR is in the right state for me to write to it. Do I? I need to check that? Suppose so. So data direction register is equal to 0. And I kind of don't like checking hard-coded values like this, but this means input mode, right? I almost feel like asserting that this is the case, but we'll see. So if that's the case, then in port A we want to write the bits, and this is where we need to read joystick, right? Now I haven't done that yet, and I'm gonna hack something together here because I just like to get something going. So I'll like map, I don't know, some keys, and I'll use SDL to get my readings. So I'll do like a read joystick buttons. And let's hack this function together. Okay, so for this, I think there's a nice little SDL function I can use for input. Let me go check my NES emulator because I did this. inputs. What did I do here? SDL get keyboard state. Let's try that. So we want to call, okay, I don't need to do this here, but I do need to call STL get keyboard state, which actually returns a certain number of scan codes. Yeah, now I remember how this works. Get a snapshot of the current state of the keyboard. Num keys, okay, parameter is num keys. If non-null, receives the length of the returned array. An array of key states. Indexes into this array are obtained by using the SDL scan code values. That's right. Perfect. Let's do that. Get the state, and then we check the state. So I'm going to hard code everything here. So if no, I'll do this differently. We'll go like this. Ain't it uint at result. So we'll set the bit here, and if I recall, it's the 4 buttons. So bit 0 is the very first button, button 1. So that'll be like, let's say I'll use ASDF. What was button 1 actually on the Vectrex joystick? Okay, it is on the left side. So that'll be A for me. What was it again? SDL scan code, right? We want to check that that value is not equal to 0. And this is not quite right. I need to be setting here a mask. So 0b, this is actually 0, but it's going to be a 8-bit mask, so I'll just do this. No, sorry, there, and there, and there, and I'll leave the rest. And let's do A, S, D, F. Okay. Oh, here goes nothing. I won't even bother debugging it just yet. Just want to see if we get anywhere. Okay, so that's not working at all. Let's see what's happening here. Interestingly, we are hitting this breakpoint. expect my result to be. See, port A is all 0. So let's see if we can get a hit here when port A is not equal to 0. And I'm using a printf here because then that'll allow me to put a breakpoint on it, even in optimized code. Oh, we do hit a breakpoint. So that's interesting. It did read my A value. I think what might be happening is I'm reading the value, but then it gets cleared before it ever gets read here. That's my guess. Or not. There's the reading of value A. From port A, I mean. Oh, port A just got an 80 in it. Oh, then that must be for rendering purposes. Okay, so that's one. Let me try different values here. Okay, that's 2. That's 4, yeah. That's 8. So it is setting those bits. Unless, wait, I'm writing, no, I thought I was maybe writing the wrong values here. This is joystick 1, and it goes in the low order bits, which is what I'm setting. Okay, so let's try this. Non-zero values in A. Oh, right, that's my printf. Okay, it's because it didn't flush until I did this. Let's turn on the trace. Let's re-enable this breakpoint. So we hit the breakpoint now, although it hasn't flushed yet here. But that's okay, right? Because we can tell it to break into the debugger. Like that. And let's see where we're at. There we go. Non-zero values in A. So where are we? F1D2. So there we are. We are here. Cool. So we should have a read buttons here at F1D5. Okay, actually reading this means the fact that it's converting to active high actually means I'm supposed to be inverting the bits. it should be all F when it's not pressed, and I should be setting them low because it will then invert. So maybe that's my problem. Although it wouldn't feel like as if... Anyway, should still kind of work, right? Not sure. So let's say we start off this at FF, and then what we do is it's basically if these are not, if they're not down, we write a 1, otherwise we write a 0 into the bit. So it's like totally the opposite. Oh, and there we have it. Okay. Holy crap, it's actually working. I mean, kinda, right? It's not really rendering everything, but we have little ships here, we have a score up here, and we have our little ship here. Oh wow, we move super fast. Ah, that's interesting. So one of these buttons is a teleport, which is not really teleporting us in the right place. Now we are turning and turning, and that's related to the fact that for analog, for the analog, it must be getting a value it's expecting like 0.5, and it's probably getting 0, so that means we're holding left, or like left and up or something, and that's why it's turning this way. One of the buttons is teleport, which right now is S here, that just keeps teleporting us in the same place. Another one, button 3 here, which is D, is a button that allows us to move forward. We move actually really fast. One of them is to fire, but we're not seeing anything fire when I fire. And the fourth button seems to do nothing. We also notice that there are no asteroids, and we're not firing. So something definitely is going on here. Let me just remove this printf here. I'll try that again. So I did need to invert the inputs for this to work. And here we can see that the scaling is not quite working for our ship there. Yeah, so it's the same thing. In fact, what looks like is happening is it says minefield 1, and it's not getting past that. This is supposed to disappear, this text. Okay, interesting. So the game is waiting on something. I would guess a timer. Yeah, I would guess that it's a timer problem, but at the same time, it is working. So let me just try something here. I'd like to try and debug just in case there's an actual... I mean, I'm not supposed to be using regular asserts, so then I don't expect one to trip, but just in case. Oh, this is Bedlam. Wrong game. Although it would be interesting to see where we get from Bedlam. and we got unhandle ops CWAY. AI, sorry. Let's CWA actually. And control code register, wait for interrupt. Interesting. But not actually what we want to look at right now, so let me just go and change this here. Let's pass it nothing so that it loads Mindstorm and debug as well. I also feel like my timing isn't quite accurate because it looks like it takes a lot longer to load here than it should. But maybe I'm wrong because maybe I'm missing the music. Okay. Okay, so this looks like it's behaving exactly the same way in debug as well. Yeah. All right. But you know what? It's cool because the input is working, so that's great. Let's see if we can get the analog to work as well. So that's here, joy analog. The joystick enable flags must be initialized to one of the following values. Ignore, return no value, return state of console 1, left right position, return state of console 1, up down position. So this is just for the, again, for the users of the BIOS to decide the joystick enable flags to tell it what it wants to read. Okay, so the joystick enable flag, C81F. But these are new flags here. Joystick enable mux flags, 4 bytes. So this is the multiplexer. I don't think it's a real multiplexer though, I think it's just from a code perspective. Maybe it is. So here we see, like, when we init OS RAM, it says init joystick enable flags, and it writes 01, 03 to the 2 bytes starting with this one, and 05, 07 to the 2 bytes starting with this. So if we go back here to top, you can see there the 1357. So 1, 3, 5, and 7. Okay. Now this is the code we're looking at. These routines read the current positions of the 2 joysticks. 1, 3, 5, and 7. So if you write 0, you want to ignore. If you write a 1, it means return the state of the console 1 left-right position. Up-down position, right? This is X and Y for the first one, X and Y for second. Joystick values are returned in 81B to 81E, where the value returned in 81B corresponds to the mask set in 81F. So on and so forth. Okay. The values are returning in where the value returned in corresponds to the mask set in C81F. But they mean this here. This is the mask they're talking about. And they're basically saying like C81B goes with C81F, and then C81E goes with C82, 0, and so on and so forth. Joystick conversion is dependent on which routine is called. So if you use Joy Digital, it's because you only care about getting a 0 if it's centered, negative if it's left, or positive if it's right, or up if center. Okay. Joy Analog, a successive approximation algorithm, is used to read the actual value of the joystick pot assigned value. In this case, C81A must be set to a power of 2 to control the conversion resolution. 0x80 is least accurate and 0x00 is most accurate. Fascinating. Decrement C823. C823. What's C823? Miscellaneous counter flagged by 0 and not in use. Set analog. Okay. So if we call this with Joy Analog, we're just decrementing the value there? Or what's the value in there? This is some miscellaneous memory cell that's used depending on the context. But here, for the joystick stuff, nobody is supposed to set it, right? Zero when not in use. Okay, so we can assume it's 0 when it's... Okay, it's probably going to clear it. Probably all the places that use it clear it when they're done. Exit C823 is cleared. Okay, so let's say it's cleared. Then this here will make it FF if we decrement it. Point to the first pot. Read it if enabled. Branch and compare X. Go back until all pots are red. Branch if not equal to that. Compare X. Branch if not equal. Clear. X points to C823. Clear it. Disable the mux. Oh, okay. So read it if enabled, and then branch to here. So here we say enable mux and select the pot. Store A. Okay, so this is what they're talking about in terms of why it's 1, 3, 5, and 7. That's basically it's a like a multiplex selector. We'll take a look again at those bits in B. Ah, right. In all cases, bit 0 is set because it needs the mux to be enabled. And then, all the values are basically there. This is like one of the axes. This is the next one. This is the next one. Oh yeah, and 0, 0 is actually 0, 0 is the first one. Okay, so it's just basically using the multiplexer again, but this time for the joystick positions. So how does it know? How does it know? Output 0 to the DAC. Disable the mux. Delay and end up with B equals to 80. Why does it say that? And then increment B. Oh no, okay. Delay and end up with B, so here we actually load 60. Oh, until it reaches 80. So increment B, branch shift plus. So keep going until we hit 80. Then check the analog flag. Branch if and it's analog. Let's say it's not. So load A 20, increment. So enable the mux, and then we do the test comparator. Test comparator. So that's what this is for. We want to check if the comparator bit is set. Branch if equal to here. Output C0 to DA. And store the result. Wait a minute. We're close. Where is it reading this value? Oh, I think I understand. Because either we're going to write C0 or 0. Okay, so one of these cases is that branch of analog. Maybe it's easier if I just read the analog bit. Maybe not. Let me see here. It's saying load A20, enable mux, test comparator. Now, if the comparator is set, we go here. If it's not set, we load 40 into B. We store that into the DAC. Test the comparator now. What does 40 the DAC do? It's like here we will write 40, otherwise we'll write C0, right? or C0. The difference is the top bit. Okay, so the idea here is that we write either this one here or these two here to figure out whether our input is negative or positive. $192, so that would be a negative value. So I think that what this is saying is that if it is positive, store B, bit A, if it's not equal, we go there. Otherwise, we go here. In which case we clear B and we write a 0. It's not equal. If it's not equal, we come here. Okay, we actually have 3 comparators, 20, 40, C0. So first we check 20. So I'm guessing this, we're talking about checking this bit here. So it's these top 3 bits that we're using to kind of access the analog values. So we check first this bit here. We read the comparator, and if it's equal, so if the comparator is set, come here, if it's not set, we put this bit here, and if, okay, so I think what I'm reading here is probably right, middle, left. I think it's as simple as that. When we're in this mode where we need to set the comparator, it's basically a mask to check which direction we're pressing. So let me just take a note of that. Notes. Inputs. Say here, analog. Looks like the way it works is that I'll just say here, bias function joy analog function reads from port A top 3 bits. So say like 7 left or up, I'm gonna guess. No, left would be negative direction, so probably down. 8 center, and then 9 will be like right or up. It's a bit of a guess. Oh no, not 8, sorry, 6, and then bit 5 here. Okay, and then the other thing I need to write is about using the mux to figure out which one we're reading. It reads port B with port B. If mux enabled, uses the mux selection bits. This here, I remember here we're talking about bit 0. 0? Is it? Yeah. If bit 0 is 0, use the mux selection bits, which is bits 1 and 2, to know which analog direction to read. And it's like 0, 0 means joy 1, mux 1x. Basically, the values are 1, 3, 5, and 7 because bit 0 is enabled. Oh, so actually, did I get this wrong? I thought the mux worked the other way around. Yeah, if it's 0 it means mux disabled. Sorry, if it's 1 it means mux disabled, right? See, the mux is enabled if that one is not set. So that must mean that I gotta figure out how like it sets up the registers to know that it's time to read for analog values, right? So here, yeah, so it does do disable mux, but then we do enable mux here. Output 00 to DAC and then disable mux, delay and end up with the BN80. Check analog flag, branch of analog pot, enable mux, it keeps saying enable mux. Maybe the idea here is it's enabling a different mux. Could that make sense? Okay, let's make some sense of this. Storing a 1 here into port B disables the mux. That's how I understand it. And yet, notice that okay, so that's interesting, right? So like actually that's when we're done. But when we actually start, we say we read X. X will initially point to let's say joystick 1 for this one here, joystick 1 for the X value, right? And then it says, okay, we've got that loaded into A, and now jump to here. And then we store that value into port B. Now that value will be, 1, 3, 5, and 7 because bit 0 is enabled. And here it says enable mux and select pot. But in this context, writing a 1 is considered enabling the mux, which makes me feel like we're talking about a different multiplexer here, a different mux for inputs. And like here, decrementing port B here would bring it to 0, which as far as I'm concerned means enabling the mux for rendering purposes, for drawing purposes. But according to this code, is disabling the mux for input code. So yes, much confusion because like the disable mux that we're talking about here is not the same one as we're talking about here. Here we really mean put a 0 in that bit 0, and here we mean put a 1 into bit 0. Very confusing, if I'm right, which I think I am. So, okay, so we delay here. Then we check the analog flag, branch of analog pot. Let's say we don't care about that, we continue with what we were doing. And then this is the 3 tests, right, that we were talking about. So we're going to check, let's say that if we're doing the X direction, are we in the positive direction? So what I think this means to me is that if I interpret the mux as being the multiplexer for the integrator and not for inputs, when it's not enabled, I can read inputs for analog and write the test comparator based on the value in A as a mask. And then yes, and then set the bit in the set the comparator bit. That's very interesting. So we read the value in A and to figure out which analog we're checking, and using that we enable or disable that comparator bit in bit B. So let's see if that makes some sense. So if I come here into update. So you know how like in here we check if integrators are enabled for every cycle? What we're interested in now is kind of like the opposite test, right?
No party without any music. Turn on the radio, huh?
Are you sure you want me to turn it on?
So like basically we say no, actually not that. That's not what I don't care about the ramp.
Okay guys, just tell me when to stop.
What I care about is the mux. This here. So let's see if my theory is right. This basically means the rendering mux, right? If it's not enabled, we're going to update analog values. So we're going to read the value on A.
Solamente porque me gusta tanto, vámonos a tocar un otro corte. Y ese es una colaboración. Pues abran las orejas para Nightcat del Norte, Nate Cloudy Mustang, Needles.
Okay. Port A. Do like a read bits with shift. Port A, we're going to read the top 3 bits, but we're going to shift it right 5 times, right? To get them, whoa, keyboard nuts there. So actually let me store that into a value. Okay, so we'll say like axis select is this. And we'll switch on the axis select. So we have 3 potential values here, right? That we care about. well, I don't know. It's more like if axis select is equal to this. So that we were saying that that was possibly right. What did I put in my notes? Yeah, right or up. Again, I'm kind of guessing a little bit here. And then this here would be center, and I think this is left or down. Okay. No, not quite. It's not really that, is it? Okay, it's some kind of multiplex again. Basically, it's a selector with these 2 bits here. Or 3 bits. 20, 40. Why isn't it 80? Why is it C0? Okay, maybe I won't do it this way. What I'll do instead is I'll just say read bits. And I will switch on. Oh, okay. Okay, I can't do it this way. Okay. Next bit position. Left shift register B. So move that bit to the left. Compare B. Check for accuracy threshold. Go back if not finished. To read the actual value of the joystick pod, a successive approximation algorithm is used to read the actual value, assign value. Okay, so when they say a power of 2, they just mean one of the bits. 80 is least accurate and 0 is the most accurate. So basically what this is going to do is it's going to set this bit, check it against port B. For not equal, it says branch to go lower. In which case it says try the next bit position, which says take that value in B and shift it left. What value in B? Okay, that's the comparator bit. So what value was placed into B initially? Before we got here. $80. It's important that we end up with 80 here. Oh, transfer B to A. Hey, ABDCW. How you doing, man? I'm trying to reverse engineer how analog input works on the Vectrex. One thing I could show you is I could show you what I've got working tonight. Which is kind of cool. I got digital input working, seemingly. So here you see, like, if I press my buttons here, I can actually change the number of players, and I can start the game. And so you saw that it was kind of like buggy the way the ship looked, so that for me means my scaling stuff's not working. And then here, minefield 1 stays indefinitely, which means that something's going on in the code and it's not finishing its loop, probably a timer-based thing. And then like here, my ship is turning, but I can press the key that would make my ship move. And the reason why it keeps rotating is because I haven't implemented the analog inputs yet, so it's reading probably a value of 0 for analog, or 1 or something. I'm guessing 0 because it's turning left over and over. And I think I need to be returning like 0.5 or something. So it turns and I can move. There is a button to do teleport, but it always teleports me back to the center. But again, like the fact that we're stuck here with minefield 1 and we don't see mines appearing, which would happen after this disappears, we're stuck in some kind of loop here. But it's pretty cool, right? Like totally getting there. See, like I just keep holding it. It's working. So we got the beginnings of input, and actually you can see here it's rendering the number of lives I have left as ships, and there's a score. So it's looking pretty good. And we're definitely getting closer. Now why we're not passing the minefield 1 here, that I'm not sure. But I figure if I can at least fix the analog, if I can make analog work, then I can sort of control my ship with my arrow keys and stuff, right? So that's sort of what I'm trying to figure out now. And I'm doing that by trying to understand how analog works. Conversion, resolution. Hey Sim, how's it going? Thanks for wishing me luck. Going pretty well. Got something going anyway. Still cool to me that this is working. It actually like does something. And also like one button's supposed to fire, but obviously I'm not firing. And I think that's because we can only fire once the minefield 1 thing disappears. Oh, so you're asking how do I get the track names to display here at the bottom? So yeah, I can tell you that. I'm using something called Snip, and I'm using Winamp. So this is more of a OBS thing there, but basically what I did is I found this thing called Snip. Snip. Here it is. So this Snip here. Okay, there we go. So Snip is this tool that supports a bunch of media players, Spotify, iTunes, Winamp, VLC, whatever. I use Winamp. And so if you click on Winamp here, you can download whatever. So I thought I was going to go down here. Basically, with that, what it does is it like watches what that tool, what that media player is playing, and it writes it out to a file. And then in OBS, you can set up a text display to display what's in that text file. So Snip is connected to Winamp. Winamp is streaming music. Snip basically takes the title and artist and writes it to a file, and OBS is set up with a what do you call it, like a text box or something, and then you can set up the text box for scrolling and stuff like that. So if you want, I can send you how I did that offline, or I mean you can just read this. So I'll put this in the chat so you can check it out. Having said that, I don't know if you saw that there's now like extensions, right, in Twitch, and I think there are extensions, maybe even in like Streamlabs or one of those extensions that have been added in the last couple of weeks that allow you to connect to something like this. So probably simpler now than it used to be. Transfer B to A, or the value that we have in A with what's currently in port A, and then store it into port A. So okay, I see. So if we think about powers of 2, right? Basically what it's doing is like if we assume that, say, it started with 1, then we shifted that to the left. So we wrote 1 to port A. So port A has 1 set. Then we shift that bit left, and then we OR it with what's in A. So that basically would make 3, right? So 2 bits set. And we store that there, and then we use that. And then after that we shift left again. So that basically is every loop we're just adding one more 1 bit to be set. That's I think what this code is trying to do, and that kind of matches up with what it says here about approximation, successive approximation algorithm that is used to read the actual value of the joystick pot. Up until the resolution that you put in here. What I'm trying to understand is what is the initial condition here? Because we branch to this section of code when we know that we want to check analog. So yeah, if we called joy analog, we decremented 0. This is negative. Therefore, here when we check the analog flag, if it's minus, means analog is set. We jump down here and start this like loop. But what I don't understand is that we jump here and we immediately test bit A against the comparator bit in port B. Port B, store A, enable mux and select the pot. Okay, so this would have been like the first time around. Clear output as the A, disable the mux. Then here, that's the thing, here we load 60 into B and it says wait until B is equal to 80, which is exactly what this is going to do. It's going to say increment B, branch if it's positive. Okay, that's why it's saying 80, because that means that the sign bit has been set. So as soon as a sign bit is set, which is when B becomes 80, then we're done with this, and then we load the analog flag, check for minus, and let's say the analog flag is set. Then we branch here, right? So that would imply that B is 80, has a top bit set. And A has 20 to check the comparator here. If branch to go lower, so branch if not equal, transfer B to A. So let's say B is 80. We just put 80 into A, 80 hex. And then what's this here? E or A. It's E or again. EOR, logical exclusive OR. So it's an exclusive OR. So we are inverting the bits with what's in A. So we take the register A and we exclusively OR its bits with what's currently in port A. So we read port A. Okay, no. What I said before was wrong. I got confused here with this 20, thinking it went with the 40 and the C0. It does not. We start by clearing, outputting 0 to port A. And when we check that, basically, I think what it means is that if it's 0 and the current input is at 0, then it will set that bit on. Like, so basically if we're not, let's say, moving left or right, the comparator will be enabled if we are looking for 0. Ah, okay, I understand. And then we set it sets, in this case, for digital input, it's going to, okay, it makes so much more sense. Basically, the value in here is just a signed value of whether we're pushing left or right. That's all. It's going to be 0 for not, because 0 is the center point, right? And if we move to the right, it's a positive value up to, let's say, 127. And if we go left, it goes probably to minus 128. It's just that. And here is just checking in terms of resolution for digital, it just wants to see, you know, are you moving all the way right or all the way left? That's what I'm seeing here. So it's checking 40 to see if we're moving, or not all the way right, like right enough. We pass a certain threshold, which is 64. And then otherwise we check the same thing, but like in the negative direction, minus 64. That's all this is. It's not more complicated than that. That's it. Sometimes I just need to be quiet and think a little bit to understand what's going on. So it's not really, there's no axis select here that I'm trying to do. But I do need to know, in terms of writing those values. Interestingly, it doesn't set the data direction here on port A as far as I can tell, even though it's going to read the value. Oh no, it only writes and then checks the comparator, that's all. Okay, so the way I'm going to see this is, if not the mux enabled, take all this out. Analog input. The mux is not enabled. We read port A to know what you're testing against. So here we're looking for no left, right. Basically, we're at center. Else, if import A is like less than 0, left or down, else right or up. Thanks, Paramvir Fagura. Thanks for the follow. Appreciate it. Okay. Now what I need to know is which one, and then that's going to be based on the mask that we were talking about. Also, I do need the mask. Let's see here. We load A with that. We store that into port B. Okay, so I need to know. Okay, I need to read port B to figure out which one we're checking. That's fine. So if the mux is disabled, then we do need to read those 2 bits to figure out which one we are interested in. Okay. So read bits of port B. And it's actually the mux selection mask. Okay, so now we're going to have to figure out which of the inputs are reading based on this. I'm just thinking, what's like the cleanest way to write this code? I'm going to check. So I'm going to be checking arrow keys for now. What's the cleanest way to do this? I want to map basically the arrow key to assigned value. Okay, another way to look at this is that basically port A acts as a mask. So what I can do is I can compute a value and then just mask it with port A, right? Does port A act as a mask? Oh, not quite. Yes, it does. It's like an OR mask. We want to OR the value. So we clear port A and we OR it with the value. It wants to know if we have a positive value. Oh no, sorry. What is this here? Oh no, it's about setting the comparator. Okay, I'm gonna kind of write this in the stupid way for now, and then we'll try and be smart about it afterwards. So what we want to set is the comparator bits of port B. I don't even think I have a thing for that yet. No. I think it was bit 6. Let me go check. No, bit 5. And then I'll say read joystick analog, and then I'll pass it the mux selection for now, and make sure it's 0. Okay, let's check my notes again. Right. So we really, right now we only care about these two cases. So if it's this, we want to check if we're pressing left or right. So what we'll do is we'll just say return. Okay, and I'm going to need this to read this here. Let's check the state, SDL scan code, left. So if the left is not equal to 0, let's return -128. Otherwise, no, not equal to 0. Yeah, that's it, right? Not equal to 0. Otherwise, if the right is not equal to 0, return 127. Otherwise, return 0. Similarly, for y, we'll check for if up is, no, let's do down, -28, and then up will be, oops, up will be like this. So we're checking the arrow keys. We're returning 0 in the case of not pressing left or right or up or down. Otherwise, we're returning the largest negative or the largest positive value. Now, if we're looking to see that 0 was set, we expect this to be equal to 0. If we're looking for left or down, it's so weird. But basically, we want to. That's why it's called, I guess, a comparator, because we need to compare the mask that's been set into port A against the value returned by the joystick, right? Yeah, I'm sure that's what I need to do is actually do it with a mask. But for now, since we're just doing it completely digitally, let's see what this gives us. Alright. If we don't handle it, just return 0. So that'll be for like joystick 2 for now. So let's see if I got this right. So let's go into the game. Okay, well, interestingly, we're not turning anymore, but we're also not really. My arrows are not doing what I was hoping. Fascinating. So interestingly, I don't hit the breakpoint. Port A. Port A is equal to 0xc8. Yeah, so we're looking for right or up. Here we're looking for center, but looks like we never looked for left or down, which is odd. Ah, yes, of course. Sine. I need to consider this as a sine value. What should I call this?
Look out! The last thing you remember before blacking out was a shadowy figure approaching in the road in front of you. You heard your sister cry out as you swerved the car into a tree. Now realize you are alone. Your sister must have gone for help. You
Okay,
find
so
yourself at the steering wheel and step out.
let's
Intent
see.
on finding your sister. You find yourself standing in front of an old mansion. It gives you the creeps. This mansion is cold and foreboding.
I mean, I'm getting close. I'm missing a little bit here about what kind of mask I'm supposed to do and how the comparator works. But the name comparator starts to make a bit more sense. There's a comparison going on between the value in port A and the value that we read from the joystick pot. Oh. Sort of working. If I push right though, I turn left, and if I push left, something's happening. Interesting. Let's see what's happening here. So this should return 0, which it does. Here, we do return 0, which means that the comparator bit should not have been set. So let's see, port B. And it's not. Same here, not set. But then when we hit the 0 one, then yes, that bit does get set. That's right. ABDCW says some progress from when I was here last time. Yeah, absolutely. Lots of progress. So you see, it's interesting. When I hold left, it does turn left, but also when I hold right, it turns left. So clearly I'm not doing the right thing here. Okay, let me think a little bit. Okay, so take another look at this code here. So here again, we want to put 0 in there. And here we test the comparator. Bit 5, okay. Enable mux test comparator. Then, if it's equal, if the comparator has been set at this moment, we just checked for 0. And if the comparator is set, it means, yep, there is no input. That's what I think that means, right? And so we're supposed to go here. Although, looks so epic with the background music. Okay, I think what I'm seeing here is that, like, if we're checking for a 0, even though it is returning that it's true, the comparator is set, it still goes ahead and checks to see now if a negative value, which is C0 here, is like -64. It wants to check now, is -64 going to return a comparator value that's true? And if it is, then it's going to store B there. It's going to store C0. That's the thing I don't quite understand. Branch if equal. So I guess the comparator should not be set if it's 0. Because, like, let's say here we tested, where is it? So we put 0 and we check. Let's say the comparator returns not, like, it's not set when we're not left or right. Okay, so let's say that's true. We check for 0 and it says not equal. Then what would it do? Then it says output 40 to DA. Then test the comparator again, and when it's not equal, we're good. Okay, so this is the case where it's supposed to write as 0. Checked for 0, it said the comparator is not set, then it checked for 40, which is 68, 64, sorry, and then it said, still not set. No, this time it is set. The hell? Wait a minute. My read joystick analog needs to return a signed value. Let's try that. Nope. Oh, that's interesting. Getting closer. It's interesting. I almost have it. Like if I hold nothing, which I would assume is 0, it's turning right. If I press left, it stops, and if I press right, it turns the other way. It's really, really close. There's just like something that's escaping me here. I'm like too tired to see it right now. Basically, I'm sure, like, based on the fact that like there's this whole logic of, you know, for accuracy and all that, it's a mask, and I just don't understand what the logic is for the mask, because I'm like too tired and stupid to see it right now. I think it's inverse the logic. Alright, look at it. We put 0, and then we're saying branch if equal, meaning that it was set. And then same thing here, we put 64, and then we check, and if the comparator is equal, if it's not equal means we're happy, otherwise if we're equal we keep going. I'm not seeing it. I'm gonna step away, let my brain chew on this a little bit, and I'm sure it's gonna be one of those things where I'll be in the shower and then it'll just come to me, you know? Yeah, of course. But I think I'm a bit tired and staring at this code for a little too long now to be able to see it. So I'm gonna call it quits. In any case, it's later than I even wanted to do this. So, but I'm pretty happy with the digital inputs that we got working, and now I just got to get these analogs to go. This is digital input, analog input. We're getting there, really getting close. Once this is working, I should be able to control my ship and stuff. I also had another thought that maybe the reason why... No, I was going to say about the stars. Like, one thing we noticed too is when the ship's going down, we don't see the stars coming out. So I'm not sure what that's about. So we'll see. But, thanks for watching, guys. And I'll be back at this in just a couple days on Wednesday night. So yeah, see you guys in a couple nights. Thanks for hanging out.